Hello everyone, and welcome back to our videos on series. In this particular video, we're going to focus on the sum of an infinite series. We've already mentioned earlier that finite series will always have a specific sum, simply because the number of terms being added is limited. In this video, we're going to investigate series that have infinitely many terms and discuss whether or not they too can have a specific sum. In order to do this, we're going to have to define for a moment what is a partial sum. So consider an infinite series of terms that I've denoted as AK, where K can take on values from 1 to infinity. So basically A1 plus A2 plus A3 and so forth. So there is an infinite, unbounded number of terms here. What we call the nth partial sum of the series, that we denote by Sn, is the sum of the terms up to and including the term an. In other words, S1 would be the sum of the terms if we stop with an upper bound of 1. So basically this would only be one term called A1. S2, so the second partial sum, is what we get when we stop with an upper bound of 2. So now k would be replaced by 1 and by 2 to transform the series into A1 plus A2. And S3 would be the third partial sum, and it would be the sum of the first three. So as you can see, the bigger the upper bound is, the more terms we are adding. These are all partial sums. Now, the nth partial sum is what we would obtain if we were to add the terms up to k equals n. So k is replaced by 1, by 2, by 3, and eventually k is replaced by n, which then determines the last term of this partial sum. So in most cases, stopping after the nth term will not give you the same total as if you had an infinite series that added other terms beyond k equals n. So these are different. However, if the sum of the infinite series exists, we suspect that Sn is going to be getting closer and closer to S as we add more and more terms. In other words, what we add beyond An will eventually become insignificant in size, so that these two series will become equal to one another. This is what we call the convergence of an infinite series. So consider the infinite series, k equals 1 to infinity, acting on a k. So in short, the sum of terms A1, A2, A3, and so on. This series converges to a fixed value called S, which is its sum, if the limit of its partial sums also converge to S. In other words, if you perform a limit on the nth partial sum and get a number called S, then S is the sum of the infinite series. In addition, if the limit of the partial sums does not exist, so for example, if it becomes unbounded or infinite, then the infinite series itself is called divergent, so it has no sum. More specifically, we're going to be interested in finding the sum of an infinite geometric sequence, or geometric series, excuse me. If you recall, we have noted in previous videos that the sum of a finite geometric series obeys a special rule. So a geometric series consists of terms where consecutive entries are r times bigger than the one that came before it. So the ratio determines if the terms are growing from one to the other, or shrinking, or maybe alternating in size. So what we found is that a geometric series counting from k equals 0 to n will exist and have a sum for all r, and it's given by the formula a0 times r to the big N plus 1 minus 1 over r minus 1. So we even proved this in our last video. So this would be the sum of a finite geometric series. So if we were to stop somewhere. Okay, so you can quickly recognize, however, that this is also a partial sum for the infinite series. So these two sequences are actually exactly the same, except for the fact that the infinite series shown at the bottom is infinite, so we would not stop adding terms, whereas in the first one we would stop once we get to a k value of n, which is the nth partial sum. So according to our theorem earlier, our statement, the sum of the infinite series, k equals 0 to infinity, a0 r to the k, will exist as long as the limit of the partial sum exists. So basically, if we can do the limit on the sum from that is acting on the summation k equals 0 to n, a0 r to the k, if that limit exists, then the infinite series sum exists as well. In other words, we need to investigate the limit of the formula we already know is the total value of the nth partial sum for geometric series. This is where we have to go back to what we discussed about sequences earlier. So when we examine sequences, we notice that any geometric sequence with an r between -1 and 1 has terms that will go to 0. But in every other case, the terms will diverge. So they'll either become infinite or will keep alternating and not specifically tend towards a value. So that makes things a lot easier for us because it means that the formula we're using will only have a specific outcome for values of r that are between -1 and 1, in which case r to the big N plus 1 will go to 0. So our formula will simply reduce to a0 over 1 minus r. In every other case, so when r is bigger than 1 or when r is smaller or equal to -1, the limit will simply not exist. So just to summarize, this means that basically the infinite series where k is counted from 0 to infinity of terms of size a0 r to the k will always converge to a0 over 1 minus r for cases where the ratio is between -1 and r. And the series, the infinite geometric series, will simply diverge, or the sum will not exist for all other cases. For example, here is a geometric series. It's an infinite geometric series with an a0 value that is 5 and with a ratio which is a half, therefore bounded between -1 and 1. This generates a series that is converging, and it will converge to 5 over 1 minus a half, which is 10. So if we listed out this infinite list of terms and added them up, 10 would be the sum of this infinite geometric series. Just to contrast, here 1/3 is the a0 term, and the ratio itself is r equals 2, so bigger than 1. Without even having to calculate the terms of this series, we know that its sum does not exist. It's a diverging geometric series. Just a quick warning, however, here's an example of a series that is of geometric type with 8 as being the constant, 1/2 as being the r. So in theory, this would be a converging series. I just want to attract your attention to the fact that here the initial number, the initial value that is given to the summation index k is not 0, but rather 3. Our formulas are not conceived to calculate the sum of infinite geometric series when k is not starting from 0. So here's a way around this. What we can do is list the terms. So when k is 3, the first number in our series, 8 times 1/2 to the 3 would be 1. And then every term that will follow will still be a half of the term that comes before it. That's guaranteed by the ratio that is a half. So now we can rewrite the series and use 1 as the initial value, as the a0. If you want, you can even change the letter of your summation index to avoid any confusion between the two things that are written. So 1 would be the A0, 1/2 would be the R, and the fact that n is now counted from 0 allows us to use our formula A0 over 1 minus R. So this series is a geometric series that converges to 2. In this last example, we're going to find the sum of a series that is not geometric, or actually we're going to attempt to find the sum of a series that is not geometric, just to show how partial sums can be used. Okay, so this is the sum where k equals 1 to infinity of ln of k plus 1 over k. So we're going to take kind of a sidestep and think of the partial sum first. So rather than going from k equals 1 to infinity, we're going to pretend we stop counting once k is n. And we're going to call that Sn for the nth partial sum. If we list out the terms of the series, so we're going to observe that we have ln of 2 over 1 when k is 1, to which we add ln of 3 over 2 when k is 2, and eventually when k is n, we'll have ln of n plus 1 over n. Now remember that properties of logarithms allow you to regroup as one single logarithm anything that was previously a sum, as long as you multiply the content of each of the logarithms. So that's what I've done here. I've regrouped all of this addition of infinitely many, or not infinitely many, but n different logarithms into one. And then I've observed that a lot of these terms are simply canceling because they're common factors. So this addition reduces to the ln of n plus 1. So basically the sum from k equals 1 to n of ln k plus 1 over k, so the partial sums that we constructed, has this total value, ln of n plus 1. The infinite series is obtained, or the sum of the infinite series is obtained when we take this partial sum and try or attempt to do a limit on its value n as it goes to infinity. In this case, what we observe is that ln of n plus 1 goes to infinity when n goes to infinity. So this series diverges. In other words, this infinite series does not have a specific sum, but it goes to infinity. Just to show a contrast, here is a situation where we have a series that is infinite, definitely not of the geometric type again. So we'll use the same strategy that we did for the logarithm a second ago. So let's examine the partial sums, the nth partial sum. If we list out the terms this time, where k starts from 1 and stops when k is n, we'll observe that consecutive terms are mutually canceling. So for every term, there's a negative term that came before it that cancels it. The only exception being the first and last terms of this partial sums. There's really just the initial 1 and the end term, minus 1 over n plus 1, that are not canceled by either something that came before or something that will come afterwards. So this is the sum of our nth first terms. It's the nth partial sum again. What happens when we don't stop at n but let that series keep adding terms? Well, actually the 1 over n plus 1 term becomes insignificant, and we get a specific limit value of 1 in this case. So our conclusion is that the infinite series 1 over k minus 1 over k plus 1 actually converges or has a total value of